At its core, a large language model is a purely probabilistic engine. It is a massive, deep neural network trained to predict the most likely next token in a sequence. It does not look things up in a database. It recalls statistical patterns of language encoded into billions of parameters. Because those parameters, or weights, are frozen the moment training completes, the model operates in total isolation. It has a fixed knowledge cutoff date and zero ability to access real-time external data on its own. This diagram maps the capabilities and hard limitations of a bare LLM. Look at the red nodes on the right. Researchers proved hallucination is inevitable. They cannot compute exact math reliably. Furthermore, a bare model cannot browse the web, verify its own outputs, or execute code. Because hallucination is a foundational mathematical property of these models, no amount of prompt engineering makes a bare LLM reliable for executing exact business logic. Traditional deterministic software sits on the exact opposite side of this spectrum. A standard Python script or rules engine executes exact computations with perfect reliability, but it fails at parsing ambiguous natural language goals. This comparative grid outlines the problem space. Real-world tasks demand both open language understanding and exact computation. Neither succeeds alone. Looking at the center column, Agentic AI covers the spread, achieving high capability across both ambiguous planning and exact execution. Agentic AI functions as a software architecture. It wraps the reasoning of an LLM around external tools using an iterative execution loop. Placing the model inside this loop allows it to take an action, read the result, and decide what to do next. That architecture transforms a passive chatbot into an active, multi-step problem solver. There is a common professional misconception that AI agents run code directly. They do not. There is a strict separation of concerns between reasoning and execution. This flowchart details the mechanism making agents possible: function calling. It acts as the translation layer to external systems. Focus on the center JSON block. The LLM analyzes intent, decides a tool is needed, and rather than guessing, outputs a strictly structured JSON object containing the tool's name and required arguments. That JSON object is an intent signal. The host application, the software harness running the agent, reads that JSON payload and deterministically fires the actual function. The computation happens safely in your Python or Node environment. It happens entirely outside the LLM's probabilistic weights. Once the host application gets a result from the database or API, it packages that real-world data and injects it back into the LLM's context window. This execution boundary is critical. The LLM handles the what and the why using probabilistic reasoning, while the rigid software harness guarantees the how with absolute precision. An AI system officially becomes agentic when it enters a multi-turn execution loop, repeating cycles of logic and action until a goal is achieved. This flowchart illustrates the react pattern: reason and act. It formalizes each iteration into 3 phases. First is the purple thought phase. The model evaluates what data is missing. Next, the teal action phase. The model selects a tool and triggers the host application. Finally, the brown observation phase. The tool result is appended. Following the red arrow, the LLM reads this and begins its next thought phase. Stripped of its abstraction, this entire cognitive architecture can be written in roughly 6 lines of Python code. It is a simple while loop checking if the model requested a tool. With every iteration, the context window grows. The model accumulates a running history of its thoughts, its actions, and the real-world observations it gathered. This React loop gives the AI the ability to course-correct. If a database query fails, the model observes the error, adjusts its parameters, and tries again, turning failures into actionable data. Early agents relied on static tool menus. Developers hard-coded the exact JSON schemas for every available tool directly into the system prompt. As tasks grow complex, forcing an LLM to memorize dozens of tool schemas burns through the token budget and degrades reasoning. The Model Context Protocol, or MCP, solves this scaling bottleneck. It uses a client-server architecture, allowing agents to discover tools dynamically over an HTTP connection. Instead of hard-coding schemas, an agent pings the MCP server at runtime to discover what functions are currently available to fulfill the request. This decouples the LLM application from fixed configurations. You can swap out databases or add new microservices, and the agent adapts instantly. However, dynamic tools introduce severe security risks. If an agent can access unseen tools, malicious users can use prompt injections to hijack the system. Strict input denial lists and validation gates must be placed between the LLM and the execution harness. Dynamic discovery allows an agent to scale its capabilities infinitely, but it shifts the engineering burden heavily onto your system's security and execution guardrails. Writing the 6-line core loop is easy. Making that loop survive a production environment without crashing or bankrupting you on API calls is the actual engineering challenge. This architecture map outlines the production lifecycle and explicit guardrails against infinite loops and context overflow. On the right, the context management column shows sliding windows and summarization to compress historical data. Finally, the bottom row details error recovery patterns to handle inevitable tool and API failures. If a service goes down, a naive loop will continuously try to call it. A circuit breaker pattern detects 3 consecutive failures and actively stops the agent from hammering the broken API, forcing it to replan. An enterprise-grade agent is defined not by its successful runs, but entirely by how gracefully it handles these external failures. The entire discipline distills down to a simple equation. Agentic AI requires 3 non-negotiable components: LLM reasoning, function calling, and loop engineering. Remove any single piece and the system breaks. An LLM without function calling is blind to real-time data. Function calling without a loop can only answer single-turn queries, and a loop without an LLM is just a rigid, deterministic script. Integrating these 3 elements changes the nature of the engineering task. Work shifts from writing linear, step-by-step logic to designing the environment for an autonomous reasoning cycle. The prompt itself is a solved problem. The ultimate bottleneck in modern AI development is the robust architectural design of the loop surrounding it. Eventually, a single agent loop hits practical limits. The context window overflows on massive tasks, and a single prompt cannot make one agent an expert. It cannot master code, data analysis, and writing simultaneously. This chart displays the next evolution: multi-agent systems. Instead of one massive loop, complex work is decomposed across specialized parallel loops. In the top left supervisor pattern, a central orchestrator delegates non-overlapping tasks to subagents, each running its own isolated React loop. To maintain stability, these agents observe strict context isolation. They communicate with each other entirely through structured JSON data, never raw text, ensuring a hallucination from one agent doesn't poison the reasoning of the others. Engineering is evolving toward the orchestration of decentralized networks of reasoning loops that cooperate to solve dynamic problems in real time.